Well, from this, how would I get, suppose I insisted, well, if someone gave it to me in that form, I don't see how I would convert it back into sines and cosines. And I'd like to show you how to do that efficiently too, because again, it's one of the fundamental techniques that I think you should know, and I didn't get a chance to say it when we studied complex numbers that first lecture. It's in the notes, but that doesn't prove anything since I don't think I made you use it in an example. So the problem is now, by way of finishing this up, to change this to the old form. I mean the form involving sines and cosines. Now again, there are two ways of doing it. The hack way is you write it all out. Well, the e to the at, a to the a plus bit turns into e to the at times sine, cosine this plus I sine that. And the other term does too. And then you got stuff out front, and the whole thing stretches over two boards, but you group all the terms together, you finally get it. By the way, when you do it, you'll find that the imaginary part disappears completely. It has to, because that's the way we chose the coefficients. So there's the hack method. Write it all out. Blah, 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 blah. And nicer. Nicer and teach you something you're supposed to know. Write it this way. First of all, you notice that both terms have an e to the at factor. Let's get rid of that right away. I'm pulling it out front because that's automatically real and therefore isn't going to affect the rest of the answer at all. So let's pull out that. And what's left? Well, what's left, you see, involves just the two parameters c and d. So I'm going to have a c term and I'm going to have a d term. What multiplies the arbitrary constant c? Answer. After I've removed e to the at, what multiplies it is e to the bit plus e to the bit. Let's write it ibt. And the other term is plus e to the negative ibt. You see how I got that? Pulled it out. And how about the d? What goes with d? D goes with, well, first of all, there's an I in front that I better not forget. And then the rest of it is I, so it's id times. It's e to the bit, e to the ibt, minus now e to the minus ibt. So that's the way the solution looks. It doesn't look a lot better, but now you must use the magic formulas, which I want you to know as well as you know Euler's formula. Even better than you know Euler's formula, okay? And they're a consequence of Euler's formula. They're Euler's formula read backwards. Euler's formula says you got a complex exponential, here is how to write it in terms of sines and cosines. The backwards thing says you got a sine or a cosine, here's the way to write it in terms of complex exponentials. And remember, the way to do it is cosine A is equal to e to the iat, ia, plus e to the negative ia divided by 2. And sine of A is almost the same thing except you use a minus sign. And what everybody forgets, you have to divide by I. So this is the backward version of Euler's formula. The two of them taken together are equivalent to Euler's formula. If I took cosine A, multiplied this through by I, and added them up, on the right-hand side, I'd get exactly e to the ia. I'd get Euler's formula, in other words. All right, so what does this come out to be, finally? This is This particular sum of exponentials you should always recognize as real. You know it's real because when I change I to minus I, the two terms switch, and therefore it's real. The expression doesn't change. What is it? This part is twice the cosine of bt. What's this part? This part is 2i times the sine of bt. And so what does the whole thing come out to be? It is e to the at times 2c cosine bt plus I times, did I lose possibly, no, it's okay. Minus, I times I is minus, so minus 2d times the sine of bt. Shall I write that out? So in other words, it's e to the at times 2c cosine bt minus 2d times the sine of bt, which is, since 2c and negative 2d are just arbitrary constants, just as arbitrary the constants as c and d themselves are, this is our old form of writing the solution, real solution. So here's the way using sines and cosines, and there's the way that uses complex numbers and complex functions throughout. Notice, they both have two arbitrary constants in them, c and d. Two arbitrary constants that you expect, but that has two arbitrary constants in it too, just the real and imaginary parts of that complex coefficient, c plus id.